In this video, we're going to go over a special type of momentum conservation problems, elastic collisions. In the first minute, we're going to talk about what does it mean for a collision to be elastic and what additional formula shows up in elastic collisions. In the next 2 minutes, we'll talk about a step-by-step approach to solving elastic collision problems. So this will especially help to someone who is lost on knowing how to approach these problems, right? Because I'll give you a step-by-step guideline on how to approach these problems. And in the rest of the video, we will spend on solving one practice problem that has to do with elastic collision. So you will see how this method applies to solving real-world problems. Okay, let's firstly start by examining, right, what is an elastic collision. So before, right, we learned that momentum is mass times velocity. We have also learned momentum conservation, so that initial momentum is equal to final momentum. Now I'm introducing another thing. Some collisions, not all, right, only if the problem says that if a collision is elastic, kinetic energy can be conserved for some of these collisions. If kinetic energy is conserved, right, that means that initial kinetic energy is equal to final kinetic energy. So that's the extra equation that I was talking about, right? Now, nothing in physics says that fundamentally kinetic energy has to be conserved. It doesn't, right? The total energy has to be conserved, but kinetic energy is only one type of many different energies. So, however, in some collisions, right, kinetic energy can be conserved, and the way you will be given that information is by when the problem tells you that the collision is elastic. Now, let's take a look how that changes our method for approaching momentum conservation problems, right? For those who haven't seen the previous video or as a review, remember that the way we approach momentum conservation problems is by sketching and drawing a diagram for the initial and final moments. So that usually means like before and after collision. Then we have to label masses and velocities of each object, right? Then we basically calculate total initial and final momentums, right? Now the additional step is that now you will also calculate the total initial and final kinetic energies, right? So in addition, so that's the third step right here. Now, in addition to setting the total initial momentum equal to each other, so you set all of your initial momentums, right, their sum equal to all of your final momentums, their sum, and you set the total kinetic energy, right, equal to total final kinetic energy. So essentially you're going to have, instead of one equation, you're going to have a set of two equations where you will have to plug in the variables and solve them. Now, so essentially we're just adding one more equation, right, to our momentum conservation approach. Now let's see how these steps, right, apply to a problem that we have on the next page. Here we have two gliders on an air track, which is a frictionless surface used in physics experiments to study motion. Glider A has a mass of 0.5 kilograms and is moving to the right with a speed of 2 meters per second. Glider B has a mass of 1 kilogram and is initially at rest, meaning its velocity is 0. The gliders then collide elastically. So here's our key to also use conservation of kinetic energy. We have to calculate final velocities of glider A and glider B after the collision. Right, so just like with the previous problems, I have made a sketch for initial situation, so before the collision, and for the final situation, so after the collision, right? Now, first let's just do momentum conservation. So initial momentum will be combined from momentum of A and momentum of B. Momentum of A is mass of A times velocity of A times velocity of B. So again, but velocity of B is 0, so therefore B doesn't have momentum, right? It's just going to be 0.5 times 2, or just 1, essentially. So that's going to be initial momentum. Final momentum is going to be mass of A times V of A, 0.5 times VA, which is unknown, and mass of B, 1 kilogram, times velocity of B. So 1 times V of B, right? Now let's set the initial momentum equal to final momentum, or essentially initial momentum is 1, final momentum is 0.5 VA plus V of B. Now, of course, we have two unknowns in this equation, which we are not able to solve. So this is where the fact that this collision is elastic comes in, right? The second part that we can do is set the kinetic energy, initial kinetic energy, is equal to final kinetic energy, right? So initial kinetic energy is going to be 1/2 mv squared. Remember that, right, only this object is only A is moving, B is 0, so it's just going to be plus 0. And final, right, is going to be 1/2 times mass of A times V of A squared plus, or V of A after the collision. Or let me call this, sorry, this initial, plus 1/2 mb VB squared. Let's plug in the value. So mass of A is 0.5, and this is 2. And this is 2 squared. 1/2 times 0.5 V of A plus 1/2 times 1 V of B. So let's simplify this a little bit, right? 1 times 0.5, all of this to the left will be 1. 1/2 of 0.5 will be 0.25 V of A squared plus 0.5 V of B squared. So just to conclude, we have now two equations and two unknowns, right? Now we have to combine these two equations together. So firstly, I just want you to register right here what happened, right? We set up the conservation of momentum, and then we set conservation of kinetic energy, right? And then I just plugged in everything that I do know, right, to get these two equations right here. I can solve these two equations in various ways. In this way, I'll use substitution. What I would advise for you to do is to solve these equations, if you can, I would advise to really solve them graphically on your calculator, because in the next few minutes you'll see that the algebra for these questions can get like a little bit complicated, right? Especially because of this square right here. So what you can do is you can just say that one of them is x and one of them is y. So for example, like one of your equation will be y is equal to 1 minus 0.5 VA or x. So you can put that into your calculator, right? Then you can rearrange this equation for y. So 1.25 x squared, right, is equal to 0.5 y squared. Then I would divide them by 0.5 and take a square root to rearrange for y. So I would plug both of these equations into your calculator, right, as two curves. So go to graph, put this one as y1, put this as the second curve, and then find the intersection of these two curves. If you're not sure how to do it, or you're not very good at the calculator, just Google like your name of your calculator, TI-83 or something, and how to find intersections of two curves. How to find intersection of two curves, right? I don't want to spend time in this video on this because this video is not on how to use a calculator, but I would say this is by far the fastest way to solve this. However, so you can pause the video, right, and actually try to solve this on your own and see if you get the same answer as I will. But for those people who are not fans of calculators, let me show you how to solve this without graphing. So once again, we have these two equations. I'm going to solve this by using substitution. So I'm going to rearrange this for V of B. So 1 minus 0.5 V of A. And I'm going to plug this over here. So 1 is equal to 0.25 VA squared plus 0.5. Instead of V of B squared, I'm plugging in the expression, this. So bear with me as we're gonna conquer this algebra, right? So again, you can rewrite this square as, so 1 point. If you forgot the a plus minus b squared formula, you can just FOIL it like this. But it's going to be 1 minus 2 times the first number times the second, so point minus VA plus 0.25 VA squared. Then we're going to open the parentheses over here, so 0.25 VA squared plus 0.5 minus 0.5 VA plus 25 times 5 is 0.125 VA squared. All of that equal to 1, which actually, let me just subtract 1 from both sides as well to make it equal to 0, right? Okay, let's combine the like terms. So I have the square term over here, which I will combine to give me 0.375 VA squared. Then I have this 0.5 and negative 1 over here. Oh, sorry, let me write this term first. And then 0.5 and negative 1 will be 0.5, right? Now, again, you could solve this quadratic equation on your calculator by graphing, right? And if you forgot how to do that, you can Google TI, the model of your calculator, right? And how to graph a parabola and find roots of the parabola. But we can, of course, use just the quadratic equation. So the two terms, right? V1, VA is 0.5 minus B plus minus B squared minus 4 times 0.375 times AC over 2 times A, 2 times 0.375. So we should get two answers, negative 0.667 for VA. And the second answer, if you do this calculation, is 2. So now plugging it back into our equation for V of B, right, which was this, 1 minus 0.5 times VA from the first root. We'll find that V of B is equal to 1.33 meters per second. Now, how come you have two answers, you might ask me, right? So which of these, how do you know which answer to pick? So notice this 2 meters per second is actually going to be the initial velocity that it had. But obviously after the collision, right, the velocity of this object changed. So therefore 2 is not going to be our answer because 2 is just the initial velocity that A already has. So really only this one is our final answer. 1.33 meters per second for B and negative 0.667 for A. So now, I know this problem was very heavy based algebraically, but I hope the overall idea made sense, right? And remember, you can simplify your algebra if you look and practice how to find the intersections of two curves, because that will cut off a lot of algebraic steps you don't have to do. Now, in the next video, we're going to go over a very important example, which is momentum in 2 dimensions. So once again, we'll go over the method for solving those problems and a practice problem. So keep practicing, keep watching these videos on your way to an A. Thank you guys for watching.